The overall goal of this procedure is to create a reference interferometer that uses whispering gallery mode sensing to detect particles with diameters on the order of tens of nanometers. For an ultra-high quality factor whispering gallery mode microcavity in resonance, photons circulate within it hundreds of thousands of times. This will cause optical properties to noticeably change when a particle lands on the microcavity. If backscattering is sufficiently strong and cavity loss is sufficiently low, a pair of split modes appear. Experimentally, this will produce the effect of frequency splitting. When particle adsorption occurs, frequency shifting will then take place.
The main advantage of this reference interferometer technique over the existing system, such as those tracking the resonance frequency of a cavity through looking at the scanning voltage, is that this is capable of suppress the laser jitter noise and therefore boost the signal by order of magnitude. Besides, this is easy to construct and cost effective.
This method is particularly suited for studying or exploiting the properties of a wide range of whispering gallery mode cavities, and for the reliable detection of single molecules like influenza A virus.
To begin assembling the reference interferometer, direct a 600 to 800 nanometer single-mode optical fiber towards the input of a 3 dB directional coupler. One of the output fibers of this coupler should form a 16-foot long series of loops, as to add optical delay.